In this video, we extend our investigation into the roots of polynomial equations to deal with quartic equations, that is, polynomial equations of degree 4. Now, in the previous video, we established the result that x squared plus y squared is equal to x plus y squared minus 2xy, and that x squared plus y squared plus z squared is equal to x plus y plus z all squared, take away 2xy plus xz plus yz. We can similarly obtain the result that x squared plus y squared plus z squared plus t squared is equal to x plus y plus z plus t all squared, take away two lots of xy plus xz plus xt plus yz plus yt plus zt. Now I'm going to leave you to provide the algebraic proof of this identity if you feel that it's necessary. Otherwise, we'll just use it later on in the video. Now, let's consider the equation ax to the 4 plus bx cubed plus cx squared plus dx plus e equals 0. And we'll suppose that the roots of this equation are alpha, beta, gamma and delta. Then the factor theorem tells me that x minus alpha, x minus beta, x minus gamma and x minus delta must all be factors of ax to the 4 plus bx cubed plus cx squared plus dx plus e. So we can write ax to the 4 plus bx cubed plus cx squared plus dx plus e must equal a times x minus alpha, x minus beta, x minus gamma, x minus delta. Now we need the a on the right hand side just to make sure that we've got ax to the 4 on the right hand side in the same way as we've got ax to the 4 on the left hand side. Now we need to think about the multiplying out of these brackets x minus alpha, x minus beta, x minus gamma, x minus delta. If you multiply x minus alpha by x minus beta, then we obtain x squared minus alpha plus beta times x plus alpha beta. And we get a similar expression if we multiply out x minus gamma times x minus delta. Now we need to multiply out these two large brackets on the right hand side. So, first of all, if we multiply the x squared in the first bracket by the second bracket, we're going to get x to the 4 minus gamma plus delta times x cubed plus gamma delta times by x squared. If I now multiply the minus alpha plus beta times x in the first bracket by the second bracket, I'm going to get minus alpha plus beta x cubed plus alpha plus beta times by gamma plus delta x squared minus alpha plus beta times gamma delta times x. And then finally I need to multiply the alpha beta in the first bracket by the whole of the second bracket, and that will give me alpha beta x squared minus alpha beta times gamma plus delta times x plus alpha beta gamma delta. We can see that we've just got one x to the 4 here. And then in terms of the x cubed terms, we've got minus alpha plus beta plus gamma plus delta, lots of x cubed. Now the x squared terms we'll need to look rather more carefully. On the top line, we've got gamma delta times x squared. Then on the middle line above, we've got alpha plus beta times gamma plus delta times x squared. and that multiplies out to give me alpha gamma plus alpha delta plus beta gamma plus beta delta, lots of x squared. And then on the bottom of the three lines, we've just got alpha beta times by x squared. So altogether, we've got gamma delta plus alpha gamma plus alpha delta plus beta gamma plus beta delta plus alpha beta, lots of x squared. Looking at the x terms, from the middle line above, we've got minus alpha gamma delta x together with minus beta gamma delta x. And from the bottom line, we've got minus alpha beta gamma x and also minus alpha beta delta x. So altogether, we've got minus alpha gamma delta plus beta gamma delta plus alpha beta gamma plus alpha beta delta, lots of x. And then finally we've got the term which is just the constant number term with no x's in it, which is simply plus alpha beta gamma delta. It's probably convenient just to reorder the x squared terms and the x terms so that the letters, the Greek letters, appear in alphabetical order. So we've got x to the 4 minus alpha plus beta plus gamma plus delta times x cubed plus alpha beta plus alpha gamma plus alpha delta plus beta gamma plus beta delta plus gamma delta, lots of x squared, minus alpha beta gamma plus alpha beta delta plus alpha gamma delta plus beta gamma delta times x plus alpha beta gamma delta. So, reverting to our previous page then, we've now inserted our expansion for x minus alpha, x minus beta, x minus gamma, x minus delta. Now we can start comparing coefficients. The coefficients of x to the 4, I've just got ax to the 4 equals ax to the 4. Not particularly interesting. So it simply gives me a equals a. Looking at the coefficients of x cubed, however, on the left hand side I've got b, on the right hand side I've got minus a times alpha plus beta plus gamma plus delta. On the left hand side I've got c lots of x squared. On the right hand side I've got a times alpha beta plus alpha gamma plus alpha delta plus beta gamma plus beta delta plus gamma delta, lots of x squared. So I've got c equals a times alpha beta plus alpha gamma plus alpha delta plus beta gamma plus beta delta plus gamma delta. Looking at the x terms, on the left hand side I've got d lots of x, on the right hand side I've got minus a times alpha beta gamma plus alpha beta delta plus alpha gamma delta plus beta gamma delta. And finally, looking at the constant terms on each side, I've got e on the left hand side and I've got a times alpha beta gamma delta on the right hand side. If I divide the first of these results by minus a, I get minus b upon a equals alpha plus beta plus gamma plus delta. If I multiply the second of these results by a, I get c upon a equals alpha beta plus alpha gamma plus alpha delta plus beta gamma plus beta delta plus gamma delta. If I divide the third of these results by minus a, then I obtain minus d upon a equals alpha beta gamma plus alpha beta delta plus alpha gamma delta plus beta gamma delta. And finally, if I divide the final result by a, then I'm going to obtain e upon a equals alpha, beta, gamma, delta. So, if we've got the quartic equation ax to the 4 plus bx cubed plus cx squared plus dx plus e equals 0 has roots alpha, beta, gamma and delta, then we know that alpha plus beta plus gamma plus delta equals minus b upon a, that alpha beta plus alpha gamma plus alpha delta plus beta gamma plus beta delta plus gamma delta is equal to c upon a, that alpha beta gamma plus alpha beta delta plus alpha gamma delta plus beta gamma delta is minus d upon a, and that alpha beta gamma delta is equal to e upon a. Now we'll have a look at a couple of examples in which we will use these results and deal with quartic equations generally. So the first example, we have the equation x to the 4 minus x cubed plus 13x squared plus 21x minus 34 equals 0, and we're told that this equation has got distinct roots alpha, beta, gamma and delta, and we're asked, without finding the roots of the equation, to determine the value of alpha squared plus beta squared plus gamma squared plus delta squared, and then we're asked what can be deduced about these roots. Well, we can straight away start by writing down the results that we know about the roots. So, for instance, we know that alpha plus beta plus gamma plus delta must equal minus b upon a. So in this case here, we've got a equals 1, we've got b is minus 1, so we've got alpha plus beta plus gamma plus delta must be minus 1 divided by 1, which just gives me 1. We know that alpha beta plus alpha gamma plus alpha delta plus beta gamma plus beta delta plus gamma delta must equal c upon a, which is 13 divided by 1, so that gives me 13. We know that alpha beta gamma plus alpha beta delta plus alpha gamma delta plus beta gamma delta must equal minus d upon a, so that is minus 21 over 1, which is minus 21. And finally, we know that alpha beta gamma delta must be e upon a, so that is minus 34 divided by 1, which is minus 34. Now we want the value of alpha squared plus beta squared plus gamma squared plus delta squared. And the preliminary result that we had right at the beginning of this video reminded us that this is exactly the same as alpha plus beta plus gamma plus delta all squared. Take away two lots of alpha beta plus alpha gamma plus alpha delta plus beta gamma plus beta delta plus gamma delta. In other words, we know that alpha plus beta plus gamma plus delta is 1, and we know that alpha beta plus alpha gamma plus alpha delta plus beta gamma plus beta delta plus gamma delta is 13. So in other words, we've got 1 squared, take away 2 times 13, so that is minus 25. So now we've got to think about what can be deduced about the roots alpha, beta, gamma and delta. So, let's at the moment think about the graph of y equals x to the 4 minus x cubed plus 13x squared plus 21x minus 34. We know that when x equals 0, y must equal minus 34. We also know that since we've got a leading coefficient, a leading power of x to the 4, we know that as x tends to plus infinity, y will tend to infinity, but as x tends to minus infinity, y will also tend to plus infinity. So, we can start a sketch of the graph for y like this. Now, the roots of x to the 4 minus x cubed plus 13x squared plus 21x minus 34 equals 0 will correspond exactly to the places where the graph crosses the x-axis. And we can see that there are going to be at least 2 such points. because the graph of y equals x to the 4 minus x cubed plus 13x squared plus 21x minus 34 is a continuous graph. A continuous graph is one that we can draw without having to take the pencil or pen off the paper. So we know that we've got at least 2 real roots. On the other hand, if all the roots were real, then that would mean that alpha squared, beta squared, gamma squared and delta squared would each be a non-negative number. So when we added them up, alpha squared plus beta squared plus gamma squared plus delta squared must certainly be non-negative. But we know that alpha squared plus beta squared plus gamma squared plus delta squared is equal to minus 25. So that tells me that there must be at least one complex root. But since all the coefficients of the equation x to the 4 minus x cubed plus 13x squared plus 21x minus 34 equals 0 are real numbers, we know from our complex number work that if we've got one complex root, then the complex conjugate will also be a root. So we now know that we've got at least 2 real roots and we've got at least 2 complex roots. But a quartic equation only has 4 roots, so we can deduce at the end of the day that this equation x to the 4 minus x cubed plus 13x squared plus 21x take away 34 equals 0 must have 2 real roots and 2 complex roots. For our second example, we have the equation x to the 4 minus 2x cubed plus 7x minus 3 equals 0 has distinct roots alpha, beta, gamma and delta, and we're going to find a quartic equation with integer roots that has roots 2 alpha minus 3, 2 beta minus 3, 2 gamma minus 3 and 2 delta minus 3. Now we saw in our work on cubic equations that the easiest way of handling such questions was to do a substitution method. So what we're going to do is try and mirror that. So we're going to say, right, let y equal 2x minus 3. If we let y equals 2x minus 3, then we've got x equals y plus 3 divided by 2. So we can rewrite the equation x to the 4 minus 2x cubed plus 7x minus 3 equals 0, which we know has roots x equals alpha, beta, gamma, delta, in terms of y, and say that the equation y plus 3 over 2 to the power 4, take away 2 lots of y plus 3 over 2 to the power 3, plus 7 lots of y plus 3 over 2, minus 3 equals 0, has got roots y plus 3 over 2 equals alpha, beta, gamma or delta. y plus 3 over 2 to the power 4 is the same thing as y plus 3 to the power 4 divided by 16. Y plus 3 over 2 to the power 3 is the same thing as y plus 3 cubed over 8. So we can say we've got the equation y plus 3 to the power 4 over 16, take away 2 lots of y plus 3 to the power 3 over 8, plus 7 lots of y plus 3 over 2, take away 3 equals 0, has got roots. Either we can write y plus 3 over 2 equals alpha, beta, gamma or delta, or we can say that y is equal to 2 alpha minus 3, or 2 beta minus 3, or 2 gamma minus 3, or 2 delta minus 3. It's a good idea at this stage to multiply the equation through by 16 to get rid of all of the fractions that we've got there, which gives me the equation now becomes y plus 3 to the power 4. Take away 4 lots of y plus 3 cubed, add 56 lots of y plus 3, take away 48 equals 0. Now if we use Pascal's triangle to do y plus 3 to the power 4, we're going to get y plus 3 to the power 4 is y to the 4 plus 12y cubed plus 54y squared plus 108y plus 81. Now you'll certainly have to do a little bit of working out on the side of your solution just to check that that is correct. Similarly, 4 lots of y plus 3 cubed is 4 lots of y cubed plus 9y squared plus 27y plus 27. And then we've still got the 56y plus 3, take away 48, all has to equal 0. Okay, if we look at the terms carefully, we first of all got 1y to the 4. Then we've got 12y cubed, take away 4y cubed, so that is plus 8y cubed. We've then got 54y squared, take away take away 36y squared, so that is plus 18y squared. We've then got 108y, take away 108y, but add 56y, so that's plus 56y. And finally, we've got 81, take away 108, which gives me minus 27, plus 3 times 56, which is 168, take away 48, which leaves me with 93 equals 0. So we've got y to the 4 plus 8y cubed plus 18y squared plus 56y plus 93 equals 0 is the equation which has roots of 2 alpha minus 3, 2 beta minus 3, 2 gamma minus 3 and 2 delta minus 3. And that concludes our short video looking at the roots of quartic equations.